Hey guys, in this lesson we would understand how to draw the graphs and how to write down the characteristics of parent polynomial functions. We can categorize polynomial functions on the basis of their degrees. So the first parent polynomial function is fx equal to x to the power of 1, that is degree 1. Second we have is fx equal to x to the power of 2. We know fx is equal to x to the power of 1 is basically the parent of a linear function. So when it's just x to the power of 1, the graph looks like a straight line passing through the origin. If it's fx equal to x squared, that's the parent quadratic function. Graph looks like a parabola passing through the origin. Fx is equal to x to the power 3 is the next parent polynomial function. The name of this polynomial function is called cubic function. The graph of this function looks like this. Next we have is fx equal to x to the power 4, that is quartic function. The graph of this function, because this is a degree 4 function, is also kind of a parabola, but this is a blunt parabola. So this is going to be somewhat like this. Next we have is the quintic function, that is fx equal to x to the power of 5. Parent function of quintic and cubic would look almost similar. It's just that this is going to be more blunt here. Variations in any of these graphs would be seen when there are transformations introduced into parent polynomial functions. For example, this is the graph of a parent linear function. There could be a graph of a linear function or a straight line going like this, going like this. So these are all linear functions, but there are variations introduced by putting in the numbers here that results in changing characteristics of the parent polynomial functions. Similarly, there could be variations for a quadratic function. For example, it can be seen like this. There are many different ways in which quadratic functions can be drawn. For example, like this, can be like this. So all these variations would be introduced when the numbers are introduced into these parent functions. Similarly, a cubic function, when those numbers, which are also called transformations, are introduced into the parent cubic function, the graph can look like this, can be like this. There are infinite ways this parent cubic function can be changed according to the introduced transformations. Similarly, when it comes to quartic functions, it can be drawn like this, it can be drawn like this. When it comes to quintic functions, variations can be seen like this. These are all quintic functions. Now, how do we make out a difference whether it's a quintic or whether it's a cubic function? We always check the number of turning points. Now, here we notice that we have 1, 2 turning points. We have 1, 2 turning points. When it comes to linear function, there is no turning point. When it comes to quadratic function, there is 1 turning point. Every time we see is a 1 turning point. Means where the graph is going to turn around. So this graph is going like this and it turns around and start going up. Here the graph is going up, it turns around and starts going down. So we would see 1 turning point. In a cubic function, we see 2 turning points. In a quartic function graph, we would see 1, 2, 3 turning points. 1, 2, 3 turning points. Whereas in a quintic function, we would notice 1, 2, 3, 4 turning points. 1, 2, 3, 4 turning points. From here, we notice that every time the turning point is there, it's always 1 less than the degree number. So when the function is quintic or 5 degree, we have 4 turning points. When the function is degree 4, we have 3 turning points. When the function is degree 3, we have 2 turning points. When the function is degree 2, we have 1 turning point. And when the function is degree 1, we have 0 turning point. So a general conclusion can be made regarding turning points is that the maximum number of turning points that can be seen in a particular function is n minus 1. Turning point is always the point where the graph turns around. Now let's find out a general conclusion for minimum number of turning points. We can write on turning points as TPs. Going back to the graphs, we see that a linear function has no turning point. So the minimum number of turning points seen here is 0. A quadratic function is only going to be called a quadratic function if it shows us a parabola. So we notice here that if there is no turning point, it will not be defined as a quadratic function, or it will not be defined as a parabola. Let's say if all the odd and even degree graphs are drawn together, So these are all odd degree graphs. This is degree 1, degree 3, degree 5. This is degree 2, degree 4. We notice that here the graph need not turn around in order to show its characteristics. Here also we notice that the graph went straight, just showing a squiggle here. Here also graph did not turn completely around. It went up like this, just showing more of a squiggle here compared to this graph. So when it comes to odd degree functions, the minimum number of turning points that we're supposed to see in an odd degree function is supposed to be 0. When it comes to even degree functions, like here degree 2 and degree 4, there has to be one turning point in order for the graph to make it look like a parabola or an even degree function. So for an even degree function, the minimum number of turning points we would always see is 1. Looking at all this, we can write on the general conclusion, and we can write down the minimum number of turning points for odd degree functions is 0, whereas for even degree functions is supposed to be at least one turning point. So when it comes to odd degree functions, turning points can be anywhere from 0 to n-1, whereas when it comes to even degree functions, turning points can be anywhere from 1 to n-1. Let's have a look at these graphs again. And now we would draw conclusions about the x-intercepts. Now for an odd degree function, the graph would always have to pass through x-intercept at least at one point. Because it's a straight going graph, therefore the minimum x-intercepts, as we also know x-intercepts are called zeros, so we can say the minimum zeros for odd degree function is going to be 1, whereas the minimum zeros for even degree functions is supposed to be 0, because these even degree functions can also be made like this without making this graph through x-intercept. Whereas when it comes to the odd degree function, if we make it like this, there will always be a point that it has to cross through the x-intercept in order to keep going straight, be it with a squiggle or without a squiggle. So we notice here is that the minimum x-intercept for an even degree function can be a 0, whereas the minimum x-intercept for an odd degree function has to be a 1. So we can conclude here, when it comes to x-intercepts or zeros, odd functions are always going to have a minimum of 1 0. Maximum zeros or maximum x-intercepts is always equal to the number of degree, and degree is represented with n. Therefore, the general conclusion for x-intercepts for odd function is the number of x-intercepts will be from 1 to n. This means if the degree is 5, we see degree as odd. So it could have 1 x-intercept, 2 x-intercepts, 3 x-intercepts, 4 x-intercepts, or maximum of 5 x-intercepts. That's why we write it from 1 to n. Now whether it is going to have 1, 2, 3, 4 or 5, that depends upon a specific question. Whereas for even functions, the minimum x-intercept that can be seen is a 0 number. Maximum x-intercepts for any given function is always equal to the degree. So the general conclusion is from 0 to n. This means if a function is degree 4, it can either contain 0 x-intercept, 1 x-intercept, 2 x-intercept, 3 x-intercept, or 4 x-intercepts. Now, which of these numbers is applicable? That depends upon a specific question. These are all general conclusions. Similarly, for turning points, if we have any odd degree function such as x to the power of 5 function, we can have 0 turning point, 1 turning point, 2 turning point, 3 turning point, or 4 turning point, because the maximum number of turning points we can have is n-1. If we have an even degree function, we can have 1 turning point, 2 turning points, 3 turning points, because the maximum is supposed to be n-1, so we have to stop at 3. Minimum is supposed to be 1 for an even degree function. Now whether the given question is going to have 1, 2 or 3, that depends upon the specific question. Now all of these functions that are drawn, they are specifically for leading coefficient positive. So all of these are positive leading coefficient. If let's say the leading coefficient would have been negative, then the graph would have looked like upside down or flipped, because Leading coefficient negative means the graph is going to reflect over x-axis. So instead of graph going up, it's going down. Similarly here as well, if we have leading coefficient negative, the graph would look like flipped upside down or reflected over x-axis. So this is cubic function with leading coefficient positive. This is quartic function with leading coefficient positive. When it is leading coefficient negative, how would these two functions look like is, it's just going to be flipped over x-axis. So this is going to be flipped over x-axis as well. Similarly here it's leading coefficient positive. When it comes to leading coefficient negative, this would be flipped around. So this down thingy will go up and up thingy will go down. And this is how the graph is going to look like. Now we already know how to make the graphs and we know how to find out the turning points and the x-intercepts. Let's write down the basic characteristics of these graphs. The characteristics that we're going to discuss here are the same characteristics that is done in the previous unit. For linear function, if we want to write on the first graphical characteristic, that is domain and range. We know domain is XER because there is no limit. Range is YER. Second is symmetry. These graphs are symmetrical about the origin. Therefore, it has odd symmetry. If we have to write down their x and y intercept, we know this is going to be 0. We do not need to mention that because we can clearly see that. Next is very important, end behavior. For writing the end behavior, we have to look at the ends of the graph. Now we notice here when a or the leading coefficient is positive, the end of the graph is pointing in the first and the third quadrant. Now what do you mean by first and third quadrant? Whenever we make cardinal axes, this is called quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So here, this is quadrant 1 and quadrant 3, where we see the ends of the graph. Whenever we have to write on end behavior, we have learned it in the previous unit that we have to go from the middle to the two ends of x-axis. So we would write down this end behavior that we are writing is for when a is positive, is if x approaches, that is here, negative infinity, y approaches negative infinity as well because it's going down. Make sure whenever we write on end behavior, we write down about both the ends. So if x approaches positive infinity, y approaches, because y is in the up section, so y approaches positive infinity. Now if you want to write on the end behavior when a is negative, that is this graph, then when x approaches negative infinity, y is going to approach, because y is going up, so y is approaching positive infinity. And if x is approaching positive infinity, that is this section, y is approaching negative infinity. So x is always defined with the left and the right side of the graph, and y is defined with up and down of the graph. Therefore, if the graph ending arrows are in either of first or the second quadrant, we would write it as positive infinity. And if it is in third or the fourth quadrant, then we write down negative infinity. Let's understand the same thing using the next example, that is a quadratic function. Here we have a positive graph is parabola opening upwards. That is, it lies in the first and the second quadrant. Both the endpoints are the ones that we look for. And when a is negative, it lies in third and the fourth quadrant. So when it comes to domain and range, when a is positive, domain is XER because there is no limit on the x value. Range is YER where y is greater than equal to 0. This is for the parent function specifically. Second characteristic we have is symmetry. When it comes to symmetry, because we see this graph is symmetrical about y-axis, so it has even symmetry. Third characteristic is end behavior. So we notice when x approaches negative infinity, that is this section, graph is in the second quadrant, so it's top. Either of the two quadrants means y is positive. So we would say y approaches positive infinity. And if x approaches positive infinity, y is still approaching positive infinity because it's in the first quadrant now. When it comes to a equal to negative, then domain is XER, range is YER, where in this case y is less than equal to 0 because it's opening downwards. Symmetry is still even because it's symmetrical about y-axis, and this is the y-axis. Third we have is end behavior. When it comes to end behavior, we look at the end points. We notice that it's in the bottom two quadrants, so y is going to be negative infinity. So we write down if x approaches negative infinity, y approaches negative infinity, and if x approaches positive infinity, y still approaches negative infinity. And this is how we write on domain, range, symmetry, and end behavior characteristics for different functions. When we're given the graphs, we can do the same thing here, and we can write on domain is XER, range is YER. When we have to write on the symmetry, it's symmetrical about origin. So looking at these graphs, we can conclude generally when it comes to odd parent degree functions, they're always symmetrical about origin. That's why the symmetry is odd. Even degree functions are symmetrical about y-axes. That's why the symmetry is even symmetry. We also notice that these are the graphs of odd degree with A positive. These are the graphs of even degree with A positive. So A positive odd degree lies in the first and the third quadrant, first and third quadrant, here also first and third quadrant, whereas even degree A positive lies in first and second quadrant, here also first and second quadrant. So the end behaviors would be same for odd degree when it's A positive. That is, if x approaches negative infinity, y approaches negative infinity, and if x approaches positive infinity, y approaches positive infinity. Similarly, the end behavior for even degree function when A is positive is when x approaches negative infinity, y approaches positive infinity, and if x approaches positive infinity, y still approaches positive infinity. And when it comes to a negative graphs in odd degree function, then the negative graphs lie from second to fourth quadrant. This is second to fourth quadrant. This is also second to fourth quadrant. So when x approaches negative infinity, y approaches positive infinity, and when x approaches positive infinity, that is the right side, y approaches negative infinity. For even degree functions, it lies in third and fourth quadrant. Therefore, when x approaches negative infinity, y approaches negative infinity, and when x approaches positive infinity, y still approaches negative infinity. So we would always notice general end behaviors for odd degree functions and even degree functions depending upon if the leading coefficient is positive or negative. We would also see similarities among their domain and range and their symmetry. So here we would see odd symmetry because it's symmetrical about origin. Here we would see even symmetry because it's symmetrical about y-axis. Domain, when it comes to odd degree, is XER because there is no limit on the x value. Range is YER as there is no limit on the y value as well. For even degree, domain is XER, whereas range is YER, where y is less than equal to 0 because it's opening downward, so it's never going to go above 0. So these are some general characteristics that can be seen in the parent functions when it comes to odd and even degree functions with different a's, being it positive or negative.